All right. Hello, my name is Jessica Carlson, and I'm a PhD student from the University of Michigan. Today I will be presenting my lab's the robot of Theseus, or Trot. This is a low-cost modular robot designed for testing the effect of morphology on locomotion. So morphology determines the function of locomotion in animals. For example, we generally assume that the cost of transport increases with the moment of inertia. However, a previous study found that cheetahs and goats have the same cost of transport despite different limb moment of inertia. This unexpected result could be due to any number of physiological differences accumulated in the 76 million years of evolutionary divergence between these two species. Because of all of the factors that differ between these two animals, isolating the effect of a single factor on performance is difficult to determine with animal experiments. In robots, we can isolate changes in one factor while keeping all of the others the same. Therefore, a modular robotic test bed can help us establish form-function relationships while controlling for interactions between factors. So which robot should we use for these experiments? Commercial robots are advertised as versatile and robust. They rarely match animal morphology, and the robot's own morphology can be very difficult to change. To address the challenges previously mentioned and to test biological hypotheses, we have developed the robot of Theseus. When designing the robot, our goals were to make it entirely customizable in both hardware and software. Trot is also designed to be very easy to fix, with most repairs taking only 20 minutes instead of months. With these goals in mind, we designed Trot to be extremely accessible. A large percent of its hardware can be 3D printed with PLA, including the gearboxes and joints shown on the left. On the right are all of the remaining parts, which can be purchased commercially. The total cost of building Trot is less than $4,000. For our software, we modified the MIT Cheetah repository, so anyone with previous experience with this code will have an easy transition to be able to use ours. We have also made a user manual and startup guide to further the accessibility of the robot. The full repository of our code is available online, and all of the software can be modified. For any structural changes, the closed-loop controller can adapt to different morphologies and gaits. We chose to use quasi-direct drive actuators, which are best for low inertia and high torque. These actuators that we have designed and built in our lab also have no elastic elements, which allow the motor to be used as a sensor to measure the torques. Even with no elasticity, the virtual spring stiffness can be changed by controlling the back drivability of the motors. In addition to these actuators, we have also attached IMUs and encoders to the robot for more data collection. Another great aspect of Trot is that the leg design is modular. Each leg can be made of 2 or 3 links, and the joints can be rotated to test knee versus ankle configurations. The lengths of the femur and tibia and tarsus links are all adjustable, allowing for the robot to test different limb ratios. The tarsus angle is also coupled to the femur via a 4-bar linkage, which allows us to increase the link count without increasing the degrees of freedom. This plot here demonstrates the range of animal leg proportions that the 2-link Trot can currently replicate. The axes represent the ratios between the femur and tarsus, and the dots on the plot represent animals that share this current configuration. The current operating window is represented within the box, which includes animals like giraffes, lions, and foxes. This window can be expanded by changing the gear ratio of the actuators. To demonstrate the modularity and sensing capabilities of Trot, we performed initial characterization experiments on 3 of these configurations, the 3 2-link configurations. Here's a video showing the testing of these configurations by having Trot walk on a treadmill at 0.1 meters per second. From this test, we are able to graph the trotting gait and the foot trajectory of these 4 configurations. As seen, even just a simple change of link ratios in the leg while maintaining the overall length of the leg was sufficient to alter the duty factor and trajectory. To test Trot's capability in biological hypothesis testing, the moment of inertia test from the start of this presentation was recreated by attaching weights on upper and lower parts of the limb, and testing to see the difference in energetic cost between these 2 configurations. As seen, there is shown to be a difference between the energetic cost when the moment of inertia is isolated. Thus, there may be other factors causing an equal cost of transport between the animals at the start. As demonstrated by its ability to isolate variables for different morphology experiments, Trot can be used to answer questions such as these. So here, I would like to thank my team, as well as Dr. Polly and Dr. Arita. In summary, we successfully designed Trot to be highly reproducible and easy to assemble with all parts either 3D printed or easily attainable. The software and design of the hardware will all be fully available and modifiable on our website. Thank you. Yes?
Can you give the specific example how the closed loop software controller to adapt to the different morphology?
Yeah, so for example, in our experiments when we were testing the different limb trajectories or limb ratios, all we had to do with the controller is to just adjust the link lengths, and then the controller was able to adapt to that change.
Okay, you mean the closed loop controller? It means like you have like, for instance, like have the feed forward and feedback control, like sum it up together, right?
Mm-hmm.
So in this case, like I mean, you modify the feed forward control contribute, or you modify like the feedback contribute.
Oh, that I'm not sure.
Okay.
But I can check.
Okay. Yeah.
Yes?
So do you use torque control or position control for your robot?
We use torque control. So then it's able, when the feet are planted with the feet to the ground, it's able to register. Yeah.
How do you do the sensing?
The sensing is mainly done with the actuators. So it's able to read what torques happen on the actuators. So that's how we're able to get like the cost of transport, because then you can get current other than the power.
So you're reading torque with back EMF or with, or you have a load cell in there?
Hmm?
Is there a load cell for the torque?
She said she measures it with current because
Yes.
current,
With
right.
current, yeah. Yes?
How fast has the lab gotten this thing to walk? Like how dynamic? Because I noticed like you have like 3D printed planetary gearboxes and stuff. Like I'm just wondering like how much you can push it.
We've gotten it up to 0.4 meters per second, but that was during a test where we weren't trying to achieve a really high speed. So I presume it could go higher, but right now, yeah, that's speed.
What is the cost of transport for the cheetah and the goat? What is the cost of transport for the cheetah and the goat?
That was taken from paper. I don't know the numbers off the top of my head, but they were, I think, around like 0.93 or something like that. But I can check.
Okay, so I'm wondering what your thoughts are on learning about trade-offs morphologically in a system that has values in the 20s compared to a biological system that has values in the zeros.
Yeah, so I guess for this case, because we're just trying to see if isolating specific variables will change the cost of transport, we haven't really looked into the comparison yet between biological and this robotic system. Yes?
Maybe a bit of a philosophical question, but you're trying to look at different morphologies, trying to be as close as possible to the animal, yet you're building a robot. What do you get from the robot that you will not get from the simulation?
I think being able to replicate certain movements, especially like within isolating the leg. So there are stuff with in biological systems like spine flexion and stuff like that maybe the robot wouldn't be able to pick up. But with the robot, you are able to kind of program it to be able to repeat movements other than from letting you data.
But you get that from simulation as well?
Yes, but in simulation, it can sometimes be harder to be able to calculate like the contact forces and stuff like that, and there is sometimes a reality to simulation gap. So with this robot, we are hoping that being able to put the model in a kind of real environment, then you can kind of decrease that gap.
Thanks.
Thanks.